Today I'm going to be explaining the difference between linear pattern and others, and I'm going to be explaining the difference between a partial variation and a direct variation. To do this, I'm going to use these four table of values to help me with my definitions. A linear relationship will show a consistent change in value for each variable, the independent and the dependent variable. Therefore, we must observe each column in each of the tables. The first column, if I look at the changes in the x values are increasing by 5 each time. The y coordinates, the y values, are increasing by 15 each time. Since the x increases by 5 every single time with no interruption, and the y's increase by 15 each time, we say that this is a linear pattern. A linear coming from the word line, meaning that when we graph this collection of data, the x and the y coordinates, it will generate a straight line. The second table shows that as the x are increasing by 3 each time, the y values will be decreasing by 60 each time. And decreasing is okay, it just means that it will be going down. This will still generate a line, it'll just be a downward trend or negative correlation, but it is still linear. The third table in my collection shows an increase in the x coordinates consistently as positive 10, but the y coordinates don't show a consistent increase. There is a pattern, but the pattern is from 4 to 8 it doubles, from 8 to 16 it doubles, and it consistently multiplies by 2 each time. Now this is a pattern, but it's not a linear pattern. This is what we call an exponential pattern because it is repeatedly multiplying by 2. In grade 9 we don't study exponential patterns. We stick more to linear patterns, but it's good to know the name of this, and it is called an exponential pattern due to repeated multiplication. For now, we will just call it nonlinear. Now our last table shows that there is definitely a pattern going up by 2's each time on the y. However, the y coordinates don't show a pattern. There is a haphazard pattern. First it increases by 5, then it increases by 1, then by 6, then by 1, and then by 12. Now remember, to be linear it has to have consistency on both variables. Since one variable, my dependent, the y, is increasing by 2 each time, but my independent is haphazard. Due to the lack of consistency in the pattern, we also call this nonlinear. Once we have decided which of these patterns is linear and which are not, we can now look at which are partial variation and which are direct variation. A linear relation that is a direct variation passes through the origin 0, 0. A linear relation that has a partial variation does not pass through the origin or the point 0, 0. To be either of these, the pattern has to be linear, which means it dismisses patterns 3 and 4. The first two are either direct variation or partial variations, as they are both linear. It should be obvious here that neither of these are direct variation. The first pattern runs through the point 0, 30, therefore making it impossible to go through the point 0, 0 also. The second pattern is decreasing from a very large number beginning with 9, 420. Well, 420, if we were to follow this back all the way to an x-coordinate of 0, it will just get larger and larger and larger because this was a decreasing relationship. If we follow the pattern back along the x-coordinates until we locate 0, and we do the same with the y-coordinates, we will reach a value of 600. Seeing that the point goes through the coordinate 0, 600 means that it does not go through 0, 0, and that also renders it to be a partial variation. Now I'm going to focus on how to create the equation of these lines. All linear relations can be written in the form above. The only thing we need to identify is the coefficient of the x and the constant. The coefficient of the x is defined as the rate of change in the pattern. We determine this by dividing the consistent changes in value that we have already found, being the 15 and the 5. Dividing the dependent change by the independent change, 15 divided by 5, we get 3. 3 is our coefficient. To find the constant, we need to look for that beginning value. The beginning value is where x has a value of 0. The y-coordinate of this point is our constant. In the first case, 30. The equation of our first linear relationship pattern is y equals 3x plus 30. And you can see that if this constant had a value of 0, that would mean that it went through the point 0, 0, and that equation would then represent a direct variation as it goes through 0, 0. For the second linear table, we have a coefficient of negative 20, and that negative 20 comes from dividing the dependent rate by the independent rate. The change in the y divided by the change in the x. And the constant would be 600, as this comes from the point 0, 600. Now we'll move on to more practical examples. So Jonathan's pay at the grocery store is shown in the table below. If we were to look at the rates of change on the independent and the dependent, the independent, the hours that he works, is going up by 5 each time. Now that's 5 hours. If a unit is involved, please make sure you include the unit. For his pay, it is consistently going up by $60. The rate at which he was paid, we divide the dependent, the $60, by the hourly rate, which is increasing by 5 hours. And when we divide that, we get his rate of pay to be $12 per hour. So Jonathan is paid $12 per hour. The equation for his pay will come in the form P is equal to a coefficient multiplied by the hourly rate plus some constant. Now the reason I used P and H here is because then it means something to the question. P referring to his pay, the dependent, and H referring to his hours worked, which is his independent. Now if we input the known values that we know, the rate of change, 12, is our coefficient. And what I need to put as my constant is where it begins from an independent value of 0, the y value, or in this case, when he works 0 hours, how much does he get paid? To find this, we need to work backwards. So even though the pattern is increasing, we need to work backwards from the hours worked of 20 all the way back to an hours worked of 0. So keeping with the pattern for hours worked, we work it back from 20 to 15, 10, 5, and 0. Similarly, we keep the consistent pattern with the pay. As it was going up by 60, we work backwards to 180, 120, 60, and 0. Finally, at the point 0, 0, we have found our constant. Inputting this, we get our equation to be his pay is 12 multiplied by his hours, of course, because he gets paid $12 per hour, his hourly rate, plus 0, meaning that if he doesn't work any hours, he doesn't get paid. This is an example of a direct variation. When I rewrote this, I didn't even put the constant because a constant of 0 really makes no change to his pay. This equation can now be used to answer questions about Jonathan's work at a grocery store. For example, if he worked 100 hours 1 month, we replace the H with 100, and we can then calculate his rate of pay. His pay will be 12 times 100, or he will earn $1,200 for the month. The alternative would be to continue the pattern from 40, 45, all the way down to 100, and increase the dependent by 60 each time, going from 480 to 540 to 600, and following all the way down, you would see that for 100 hours he does earn $1,200. Using the equation is a lot simpler. Similarly, if we knew that Jonathan was paid $864, we could solve for the amount of hours that he worked that month. Now we replace his pay with 864 and solve for h. First dividing both sides by 12. We get h to be 72. If Jonathan works 72 hours in a month, he will earn $864 at the grocery store. Now let's take a look at Mary's situation on the right. The chart shows a linear pattern. The distance in kilometers increases consistently by 50, while the cost of the rental van increases by $20. The coefficient of the cost equation will come from dividing the rates of the cost by the rate of the distance, which of course gives us 0.4 dollars per kilometer, or 40 cents for each kilometer that she drives for the rental. Remember to always divide the dependent by the independent. And again, to find the constant, I'm looking for the dependent value that goes with an independent value of distance of 0. I will work backwards with my pattern. When I do, I get a starting value of 0.25. My constant is 25. This refers to this rental being $25 just to rent the van, and the 0.4 coefficient refers to it costing Mary 40 cents for each kilometer that she drives the van. So when you rent a car, it costs you $25 up front, but it's 40 cents for each kilometer that you drive it, both attributing to the total cost of the rental. This cost equation can now be used to find the cost of driving a certain number of kilometers, or finding out how many kilometers I could drive for a certain amount of cost. If Mary only had $60 to rent the van, how far could she drive? Inputting the 60 in for cost, we get this equation. To solve, we first subtract 25 from both sides. Then we divide both sides by the coefficient of d to isolate the d itself, telling us that Mary can only rent the van to drive a distance of 87.5 kilometers if she only has $60 to spend. As a summary, first, identify if the pattern is linear or nonlinear. If it is linear, you need to look at the rate of change to find the coefficient of the independent variable. Then locate the point where the independent value is 0, and that will be your constant. If the constant is 0, as in Jonathan's case, it is a direct variation. If the constant is not 0, because the pattern doesn't go through 0, 0, as in Mary's case, it is a partial variation.